Hello and welcome to this presentation. My name is Isaki Keke, a graduate student at Texas Southern University. This is project number 2 for CS583 data mining. In this presentation, we are going to discuss about the clustering through decision tree construction paper that was written by Bing Liu and Yevyuan Xia from School of Computing, National University of Singapore in Singapore, and Philip S. Yu from IBM T.J. Watson Research Center in New York, USA. In the presentation, we will talk over the key contribution of the paper as well as analyze algorithm outlined in it. In performance evaluation of algorithm, we will also outline some key takeaways and shortcomings of the paper and the algorithm. To start with, the paper outlines some shortcomings of the clustering algorithm. But first, let's find out what is clustering. According to Wikipedia, clustering is the task of discovering groups and structure in the data that are in some way or another similar without using known structures in the data. The authors of the paper, however, define clustering as an important exploratory data analysis task that aims to organize objects or the data records into similar groups, which are called clusters. We will see how it is indicated in the paper that most clustering algorithms fail to address issues in the clustering process that are very important to achieve uniform or realistic clusters or data organization. But before proceeding, note here that the author point out that clustering has often been referred to as an unsupervised learning, because no class labels denoting an a priori partition of the objects are known. And obviously, supervised learning will be such that records are already labeled with known classes. So why did they write this paper? The main objective of the paper, as presented by Bing Liu et al., is to propose a clustering technique, which, in contrast to the existing notion that clustering is an unsupervised learning, the author's technique, called CLTree, is based on a supervised learning method known as the decision tree construction. You're going to ask, what is CLTree? CLTree stands for clustering based on decision trees, CLTree. So you see the CL comes from clustering and the rest of the word tree comes from the trees without an S. The authors single out the fundamental difference of CLTree from existing clustering techniques is that the existing procedures form clusters explicitly by grouping data points using some distance or density measures, while their method finds clusters implicitly by separating data in empty regions using a purity function based on the information theory. They, however, say that other techniques also have some advantages over CLTree, as there is no one method that has all the advantages. So CLTree has some advantages over the other methods, and the other methods also have some advantages over CLTree. Let's look at some of the major advantages of the CLTree. We see that CLTree is able to find the natural clusters because its tree building process classifies the space into data in empty space regions without making any prior assumptions or using any input parameters. Most existing methods require the user to specify the number of clusters to be found or the density of thresholds. CLTree is also able to find clusters in full dimensional space as well as subspaces. Many other algorithms that work in full spaces do not work well in subspaces of high dimensional spaces, and vice versa. It also provides description of the resulting clusters in terms of hyperrectangular regions. Common clustering methods only group data points together and give a centroid for each cluster with no detailed description. The CLTree algorithm also comes with a very important byproduct, the empty regions. Although clusters are important, empty regions can also be very useful. For example, in a marketing application, clusters may represent different segments of existing customers of a company, while the empty regions are profiles of non-customers. Knowing these profiles of non-customers allows the company to probe into the possibility of modifying their services or product to target these particular spaces of the non-customers. It also deals with outliers very effectively. It separates outliers from real cluster because it naturally identifies sparse and dense regions. Now, CLTree has several steps to be for its implementation. You can see that some of the basic steps here is that you have to build a cluster tree. It also introduced the endpoints. You had the modification of the decision tree. They use the new criteria. They use a new criterion. They have a modification on the criterion that is applied on the algorithm, and also you can. They have a way to. They have a different way that you use for pruning the cluster trees as well as simplifying the clusters. Now, looking at the technique, first we look at building the cluster trees, and specifically the decision tree. We know that the objective of a decision tree is to partition data into different classes. Considering the example given on this paper, the 4 hyperrectangular regions in a figure are produced by a tree, the one on your left right here. A region represented by a leaf can also be expressed as a rule, like shown in the diagrams. And on the right-hand side, the upper right region can be represented by x is greater than 3.5 and y is greater than 3.5 approaches to O, which is also the rightmost leaf. In the process to build such a tree, recursively use divide and conquer strategy to partition the data. All the same, information gain is still commonly used to choose the best cut. Now, the modification done by the authors to the decision tree construction has 3 parts. They introduced endpoints in the data region. In the given data set, uniformly distributed non-existing endpoints are added. These are not physical points, but these are just imaginary, if you can say, points that are added to the data set. And the number of endpoints added can be determined by the endpoints added algorithm that is shown here, where it is basically the same as the number of y points in the beginning. As the tree branches, endpoints are distributed equally until y points are determined. The endpoints will be increased to match the number of y points. Just a point to note here that a 1-to-1 ratio of y and endpoints is not necessary, but this is a preemptive move in case you run into situations where there may be too few endpoints left after some splits. So you add the endpoints to match the y points. So whenever you run into so many y points, you kind of want to add the endpoints to match whatever the y points are. Another modification is done to the decision tree algorithm where the number of endpoints are computed on the fly, and also evaluations done on both sides of the data points. Evaluating both sides of data points accommodate the situations that are not covered by the tradition evaluating one side, which may have less or none to evaluate. Looking on yet another modification the authors have is with the criterion. Normally, decision tree building for classification uses the gain criterion to select for best cut. Now, according to Liu et al., this is not satisfactory because the cut with the best information gain tends to cut into clusters, and the criterion does not anticipate the best cut, where this problem causes severe fragmentation of the clusters and loss of data points. So the authors designed a new criterion, although still uses information gain as the basis, but has the ability to look ahead. They get the first cut using gain criterion, then they look ahead at most 2 steps ahead to find a better cut that cuts less into the cluster region. Now, looking at this algorithm here, you can see they find the initial cuts and line 2 specified. That's how you get your initial cuts. And on lines 3 and 6, the algorithm looks ahead to find the better cuts. As we have we talked about earlier, that it uses the initial cut, it uses the normal gain, and then it looks ahead for the best cut. So lines 5, 7, and 10 finalizes the algorithm. They compare the relative densities, and the one with the lowest is chosen as the best cut overall. As you can see in this diagram here, where it suggests the cuts are more efficient, that you can see the cluster are cut into efficient cuts. The second thing mentioned by the authors of CLTree algorithm is the pruning of the cluster tree. The problem they found with other common methods was that with the recursive partition of method of building cluster tree will divide the data space until each partition contains only a single class or there is no improvement, which leads to a complex tree that partitions the space more than necessary. Since clustering is a good or bad, depending on the application and the user judgment, Liu et al. Use subjective measures for pruning, in which there are two interactive approaches. One is browsing, where the user explores the tree to find a meaningful clusters, any cluster that makes sense to them. And also, the second will be the user-oriented pruning, where users specify two parameters. One for the minimum number of Y points that the region must contain, and the other to specify whether an N region should join an adjacent region to form a bigger cluster region. Now this one is an algorithm here where it recursively runs down the tree and then goes back up level by level to determine if clusters should be formed by Y nodes or by joining two neighbor nodes. So you see here, if two subtrees below a node can be pruned, the algorithm assigns a true to the stop field, and the stop field of the data structure, or otherwise it assigns a false field. So that means no joining, or the pruning doesn't occur there. Now let's look at the performance of the CLTree algorithm as implemented by the authors. With regards to performance, they did the test with the algorithm to determine its ability to be efficient and be accurate as well. Just to note that these experiments were performed notably on a very low-end machines. They used a Sun E450 with a 250 megahertz processor and 512 megabytes of RAM. They did the experiments on both synthetic as well as real-life data. However, in the paper, they explained that due to space constraint, they only show what was done with the synthetic data. During this evaluation, looking at efficiency, where they needed to determine how the execution time scales with dimensionality of clusters, size of data sets, dimensionality of data sets, and number of clusters in the data space. Now here we can see that when data is uniformly distributed, CLTree takes less time to build a tree because of the ability of CLTree to naturally find hyperrectangular clusters. They also needed to test about accuracy. This is where you test if the algorithm finds clusters in subspaces in high dimensional space and how accurate it is with different pruning parameters. So here the graphs indicate that in this experiment it shows that all data points in the clusters are found for both 5 and 10 clusters, as well as their dimensions are also recovered, even in cases where there is low density regions around the cluster boundaries. In conclusion, after reviewing the paper by Liu et al., we see their proposal of a CLTree algorithm in that they have successfully demonstrated why this algorithm is important and is needed. They also show its functionality, outlining the steps of the algorithm, and they break it down step by step. They also show its stability, which was accompanied by examples and tests performed to prove that the algorithm is efficient and very accurate. And also they also pointed out how it can fit in the whole clustering segment of the data mining, noting that it is not the best algorithm or the only algorithm to be used in clustering, but it can be used in conjunction with other algorithms as well. And with that, I conclude my presentation. Thank you very much for watching, and have a great day.